So welcome you to this lecture. So what we have been doing so far was looking at the notions of sufficiency and minimal sufficiency. Then we talked about a notion which is very complementary to the notion of sufficiency, which we named as ancillary. We say a statistic T is ancillary if it does not contain any information about theta, or in other words, its distribution does not depend on theta. So it is complementary to the sufficiency in the sense that sufficient statistic contains all the information about theta, whereas ancillary statistic does not contain any information about theta. This notion of ancillary led us to the concept of completeness, and we talked about the completeness of a family of PDFs. I say a family of PDFs f theta, theta belonging to capital theta, is said to be complete or boundedly complete if for any function psi or for any bounded function psi, depending on whether we are talking about completeness or a boundedly completeness, if for any function psi, which is either bounded or any function psi, expected psi x equal to 0 implies that psi x is 0 with probability 1. So of course, every complete family is boundedly complete. Converse may not be true. That means a boundedly complete family may not be complete. And I gave you an example, which I'm leaving you as a homework problem. And this would also be a part of your homework number 3. Now I can talk about the notion of completeness for a statistic. A statistic T is said to be complete or boundedly complete if the family of distributions of T is complete or boundedly complete. Then let us do this example. Let x1, x2, xn be IID, Poisson, theta, random variables. Find a minimal sufficient statistic for theta and check if it is complete. So there is one example of a Poisson. The second example is for binomial. In both the cases, you have been asked to find a minimal sufficient statistic and check whether it is complete. Then the next example, which I consider, is about uniform 0 theta. So let me use the whiteboard so that you can understand how to do these problems. Let me use the whiteboard. So the first example which we were considering was x1, x2, xn is IID Poisson theta. Theta is greater than 0. You have to find a minimal sufficient statistic and check if it is complete or not. So let us look at f theta of x1, x2, xn, which is a joint PDF of x1, x2, xn, which is, in the case of this, would be product of all this, so e to the power n minus n theta, product, sorry, it is the same theta, so theta to the power summation xi, by product of factorial xi, if xi is between 0, 1, 2, so on, and this is 0. So I try to write down this. This can be written as so I try to look at for sample points for x and y belonging to the sample point. That means xi and yi takes value 0, 1, 2, so on. I try to see when f theta x upon f theta y is independent of theta. So when I look at f theta x upon f theta y, it gives me product factorial yi divided by product factorial xi. E to the power minus n theta gets cancelled, and then theta to the power summation xi divided by theta to the power summation yi. This will be theta to the power summation xi minus phi. Now, this would be independent of theta if and only if what happens? Now, note that as long as it has a positive power or any power different from 0, this whole quantity is going to depend on theta. So this would be independent of theta if and only if summation xi is same as summation yi. That means Tx is equal to summation I is equal to 1 to n psi is minimal sufficient. Now I have to check whether it is complete or not. For that, I need to know what is the distribution of T. I know that if x1, x2, xn are IID, then Tx has Poisson and theta. Because I know that Poisson distribution has reproductive property. So Tx would be Poisson and theta. So what I have to check for completeness? Let psi be a function such that expected value of psi t is 0 for every point in the parametric greater than 0. Right? My parametric space is any theta greater than 0, so this is for every theta greater than 0. What does that mean? Let me write down over here. That means this is same as T has Poisson and theta. So this is same as summation j is equal to 0 to infinity. Psi of j e to the power minus n theta. PMF of Poisson and theta to the power j by factorial j. This is 0 for every theta greater than 0. What does that mean? E to the power minus n theta goes outside. That means summation j is equal to 0 to infinity. Psi j n to the power j by factorial j theta to the power j is 0 for every theta greater than 0. But what is this? This is a power series in theta. Because it is kind of a it is of the type summation aj theta to the power j. So it is a power series in theta. Now I have seen that what is given to you, a power series, vanishes on the whole positive part of the real line. And I know that if two power series match in an open interval, then the coefficients of the two power series should be same. In particular, if a power series vanishes in an open interval, then all the coefficients should be 0. So this implies that psi j n to the power j by factorial j is 0 for each j is equal to 0, 1, 2, so on. What does that mean? That means psi j is 0. But Poisson distribution, you know that psi has Poisson distribution only takes value 0, 1, 2, and so on. So that means this implies that probability that psi t is 0 is 1 for every theta greater than 0. Because for whatever theta may be, t only takes value 0, 1, 2, and so on. So psi t will T is complete. Because to show that T is complete, what I have to show? If I take any psi with respect to psi t is equal to 0, that should imply psi t is equal to 0 with probability 1. And that is what is being done over here. Now I can look at the binomial example. Suppose x1, x2, xn are IID binomial and theta. Theta is between 0 to 1. M is a known positive integers. M is known to you. So when I look at f theta x, joint PDF of x1, x2, xn, so it is a product of each of them. So it is product I is equal to 1 to n, m choose xi. Theta to power xi, and because of this product, it will become theta to power summation xi. And 1 minus theta to power m minus xi, and with product, it will become theta to power mn minus summation xi. All right? So this can be written as product I is equal to 1 to n, m choose xi, theta upon 1 minus theta to power summation xi into 1 minus theta to power m. I have to find the first minimal sufficient statistic. So for any 2 points in the sample space, what is your sample space? Collection of all those x1, x2, xn such that each xi is between 0 to m. What is your sample space? Because it is a binomial, there are n binomial independents. Each ti is from binomial m theta, so each ti is from 0, 1 to I. This is your sample space. I look at f theta x upon f theta y, which is product m choose xi divided by product m choose phi I, then theta upon 1 minus theta power summation xi minus summation phi I. 1 minus theta to power mn gets cancelled, so is independent of theta if and only if. Now note that as long as this theta upon 1 minus theta to power has some power, as theta varies, this quantity is going to depend on theta. So this would be independent of theta if and only if summation xi is same as summation yi. So that means Tx, which is summation xi, is minimal sufficient. So I have to see whether it is complete or not. For that, I need to know the distribution of summation xi. Summation xi I know is binomial. Each xi is binomial m theta. So summation xi would be binomial mn theta. So expected value of psi t is equal to 0 for every theta belonging to 0 and 1 implies what? This would imply that distribution of t is binomial m theta, so summation j is equal to 0 to mn. Mn choose j, theta to power j, 1 minus theta to power mn minus j is 0 for every theta belonging to 0 to 1. What does that mean? Theta upon 1 minus theta to power mn, sorry, theta upon 1 minus theta to power j, not mn. Mn goes separately and that comes outside the sum, and since it is 0, so this would imply that this is for every theta belonging to 0 to 1. Let me use the next. See, so what I have got is summation j is equal to 0 to mn. Mn choose j, theta upon 1 minus theta to power j is equal to 0 for every theta belonging to 0, 1. Let me write theta upon 1 minus theta as t. Now, what kind of a function it is? This can be written as, so t is -1 plus 1 upon 1 minus theta, right? -1 plus theta. Yeah. So you can see that this is, what kind of function is 1 minus theta is a decreasing function. So 1 upon 1 minus theta is an increasing function. And it is a continuous function. So if theta lies between 0 to 1, t can belong to theta is equal to 0, it takes value 0, and theta is equal to 1. And as theta takes all values between 0 to 1, t will take all values between 0 to infinity, because t is a continuous function of theta. Theta upon 1 minus theta is a continuous function. So by intermediate value property, if theta is taking all values between 0 to 1, t will take all values between 0 to infinity. So what I get from here, then that means is j is equal to 0 to mn. Mn choose j, t to power j is 0 for every t belonging to 0 to infinity. What is the left-hand side? It is a polynomial of degree mn. So what is given to you? A polynomial of degree mn is 0 for every t 0 to infinity. That means this polynomial has infinitely many roots, because it is 0 for every t belonging to 0 to infinity. But you know that a polynomial can have at the most, a non-zero polynomial can have at the most mn roots. Since this is having infinitely roots, that means this polynomial itself has to be 0, which means each of the coefficients have to be 0. Sorry, I have missed my psi everywhere. Let me check in the previous case, because this would be expected value of, yeah, so I missed psi t is equal to 0, so there has to be psi over here, psi of j. So this would be psi over here, because I am saying expect to psi j is 0. Psi t is 0, so psi. So that means each of the coefficients of this t would be 0. That means psi j into mn2's t 0 for each j from 0, 1 until mn. This implies that psi j has to be 0 for j is equal to 1 to mn. But t only takes value 0, 1, mn, because t is binomial mn, theta. So this means probability that psi t is equal to 0, 1, because t can take only value 0, 1, 2, mn. And for t, 0, 1, mn, psi t is 0. So this would be 0, whatever theta may be. So this proves that t is complete. Now I can go to the next example, which x1, x2, xn are ID. Let us say uniform 0 theta. Then I know that f theta x is 1 by theta to the power n, and indicator that, first of all, each xi should be greater than or equal to 0. Indicator that xi is greater than 0. Product. And then each xi less than theta, so that can also come as a part of our indicator that xn is less than theta. So if you look at two sample points, f theta x and f theta y, is independent of theta, because 1 upon theta to the power n will get cancelled, and you'll be left with the indicator theta greater than xn, indicator theta greater than yn. So they would be independent of theta if and only if xn is as yn. So that means Tx is equal to Xn is minimal surface area. Now to see whether it is complete, I have to know the distribution of P. So what I know is Fxn theta. The PDF of Fxn theta, general PDF of RS order statistics, I know, based on a random sample. So I know what is the PDF of R. This is same as n times distribution function. Distribution function of uniform 0 theta is x by theta, or n minus 1 into density, which is 1 by theta. 0 less than x less than. So this becomes x and x. This becomes n x to the power n minus 1 by theta to the power n of 0 less than x. Now, expected value of psi of xn 0 for every theta greater than 0, because my parameter space is theta greater than 0. What does that mean? That means 0 to theta n x to power, sorry, psi x, so write it down, n x to power n minus 1, theta to power n dx 0 for every theta greater than 0. That means 0 to theta psi x into x to power n minus 1 dx is 0 for every theta greater than 0. What you're having, your integral is 0 over every Borel set. And there's a standard result which says that if your integral is 0 over every Borel set of the type 0 to theta, then psi x has to be 0. Otherwise, also you can differentiate it, because if this is 0, then derivative is 0. Of course, for differentiation, you would assume that this is a differentiable function, which may not be true. It will be a differentiable function if psi x is continuous. But even if psi x is not continuous, if psi x is continuous, then anyway, this implies its derivative is 0. So because function is 0 that for every theta, that means its derivative would be 0. So psi theta, theta to the power n minus 1 would be 0. So that means psi theta is equal to 0. Otherwise, also if psi was not continuous, then there is a result which says that if integral a to b x dx is 0 for every b greater than a, in the measure theory, which you can remember. So this would be, this is equal to 0 would imply that psi theta is 0 for every theta. 0. That means psi t is 0 for every t greater than 0. But uniform 0 theta, whatever theta may be, always takes only value in 0 to theta. So if psi t is 0 for every t greater than 0, probability that psi t would be 0 would be 1 for every theta greater than 0. Because under theta, distribution is uniform 0 theta. Uniform 0 theta, t takes only values between 0 to theta. But I know that psi t is 0 for any t greater than 0. Psi t would be 0 for t between 0 to theta also. This proves that t is complete. So I showed you 3 examples where you could show that your statistic is complete. Let me come back to my notes again. So I could do this example, the first 3 examples I could do. Now, let x1, x2, xn be normal 0 theta, where theta belongs to infinity, because theta is a variance, so variance has to be positive. So that is why theta takes value in 0 to infinity, so that t1x equal to summation xi is not complete. That is very clear because you can just see summation xi has normal 0 and theta. So let me call this as T1. But to show that it is not complete, what I have to show? The summation xi has a mean 0. So expected value of T1 is 0 for every theta greater than 0. So I found a function of T1, which is a identity function x, is 0 for every theta greater than 0. But what is the probability T1 is equal to 0? T1 is a continuous random variable. Summation xi has a normal 0 and theta. So continuous random variable taking a particular value z would be 0 for every theta greater than 0. Whereas you wanted this probability to be 1 if T1 was complete. So this implies that T1 is not complete. Now, to show that T2 is complete, what you need to show is, what is the distribution of T2x? T2x is T2 by theta is chi-square on n. So T2 is theta times chi-square on n. What does that mean? The PDF of T2 is how much? 1 by 2 to the power n by 2, gamma n by 2. So you have to show the expected value of yeah, somehow this is dropping all the time. So let me just continue with where I was. So expected psi of T2 will be psi of t e to the power minus t by 2 theta and t to the power n by 2 minus 1 dt is 0. Because this is constant, theta to the power n by 2 is constant, and that gets consumed with 0 every theta. But what is this? There is a e to the power minus t by 2 theta. So it is kind of a Laplace transform. And Laplace transform is 0 in an open interval. So what it means is a Laplace transform of the function psi t to the power So this would imply that psi t, because Laplace transform is 0 in an open interval, that means psi t into t to the power n by 2 minus 1 would be 0 for every t greater than 0, which implies that psi t would be 0 for every t greater than 0. But T2 has a chi-square distribution. So it takes only positive values with probability 1. So probability that psi T2 is equal to 0, because psi t is 0 for every t greater than 0. So probability psi T2 is equal to 0 would be 1 for every theta greater than 0. That proves that T2 is complete. Now I see a question in the chat box which asks, can you repeat why T1 is not sufficient in case of normal distribution? I did not say that T1 is not sufficient. What I said was, if I look at the model x1, x2, xn normal 0 theta, where theta belongs to theta, so that the statistic T1 is not complete, where T2 is complete. So T1 is neither sufficient nor complete. What I was trying to show over here was that T1 is not complete. If T1 was complete, what does that mean? T1 would be complete if for any function psi, expected value of psi is equal to 0, should imply probability psi t is equal to 0 is 1. What I have to show? I should find at least one function psi for which expected value of psi is 0, but psi is not 0 with probability 1. And that is what I'm trying to do over here, because T1 summation xi has a normal 0 and theta. I look at the function psi T1 as T1, then expected value of T1 is 0 for every theta greater than 0, because its mean is 0. So I found a function of T1 which is 0 for every theta greater than 0. But what is the probability that T1 is 0? What is the probability that psi T1 is 0? Psi T1 is T1. So what is the probability T1 is equal to 0? T1 is a continuous random variable. It is a normal. The probability that it takes a fixed value would be so if T1 was sufficient, since T2 is minimal sufficient, T2 should have been a function of T1. But you cannot get summation xi squared from summation xi. So T1 cannot be sufficient. Now let's look at this example. Let x1, x2, xn be IID normal theta, theta square, where theta takes value in the real line, so that summation xi square is minimal sufficient, but not So I leave this as an exercise. Then you can do this example also, x1, x2, xn be IID. So let me do this one, normal theta, theta square. Let me use the whiteboard. So x1, x2, xn, IID, normal theta square, where theta can take any value in the real life. Then what I have to show is Tx is summation xi and summation xi square is minimal sufficient, but not complete. Actually, reason why it will not be complete is because here theta and theta square is coming. So I can play around. So I can get theta through a expected value of this, and I can also get theta through expected value of summation xi. So I can find a function whose expected value is 0, then the probability that that function would be 0 is not 1. But first try to prove that it is minimal sufficient. That we have already seen. If I look at f theta x is 1 by sigma. 1 by sigma is mod of theta. So let me put here theta greater than 0 so that you don't have. So 1 by theta root xi minus theta whole square. So summation xi square by 2 theta square minus 2 theta summation xi by xi, and then e to power minus n theta square by theta, so bar n. So there will be something of this kind. So if I look at the two sample points f theta x upon f theta y, this would be e to power 1 by 2 theta square summation yi square minus summation xi square plus 2 by theta summation xi minus summation yi. This would be independent of theta, which implies that theta square comes over here and theta square. So that means summation xi minus summation yi theta square two times summation xi plus theta times summation yi square minus summation xi square is independent of theta. Now, what is this? These are polynomial. Saying polynomial is independent of theta. That means this would be 0. So this doesn't depend on theta, because for theta nearing 0, it is 0. So this would be 0. Or it doesn't depend on theta. See, if it doesn't depend on theta, its derivative will also not depend on theta. Its double derivative will also not depend on theta. So triple derivative will also not depend on theta. So if you take the triple derivative, first derivative would give you 2 times summation xi y minus theta. The second derivative will give you summation xi minus yi times constant. So that does not depend on theta, so that means summation xi. That is zero actually. Any derivative is zero because it is independent of theta. First derivative, second derivative, all derivatives are zero. So I take the second derivative. Second derivative gives me summation xi minus yi with a constant term. That is zero. That means summation xi minus yi is zero. But once summation xi minus yi is zero, it gives me summation theta times summation yi square minus xi square does not depend on theta. That also gives me summation yi square minus summation xi square. So this means summation xi square is same as summation yi and summation yi square. So that means tx summation xi square is minimal sufficient. So let me call this, I have to show that it is not complete. So Tx I can write down as T1x and T2x, where T1 is summation xi and T2 is summation xi. I know that each xi is normal theta. So first thing I know is summation xi minus x bar whole square. If I look at expected value of summation xi minus x bar whole square, this is same as n minus 1 times theta square, because variance is theta square. Now I try to get expected value of T1 square. So expected value of T1 square is how much? That is summation xi I know is normal. T1, variance of T1 is n theta square, plus expected value of T1, which is n theta whole square. So what do you get? This is n plus n square. N into n plus 1 theta square. So what do you get from here? Expected value of, this is same as summation xi square. Summation xi square is same as T2 minus n times x bar square. X bar is nothing but T1 upon n. So n times T1 square by n square, so that is T1 square by n. And I subtract minus T1 square upon n into n plus 1. So what I do is I try to subtract that. So expected value of 1 upon n minus 1, summation xi minus x bar whole square, minus T1 square upon n into n plus 1 is 0 for every theta greater than 0, because both are theta square. So theta square minus theta square. But what is this? This is same as expected value of 1 upon n minus 1 summation xi square, which is T2 upon n minus 1. Minus, this would be n x bar squared, so minus n upon n minus 1, but x bar is same as T1 upon n. So T1 square upon n square. So this would become 1 upon n into n minus 1 T1 square. Minus T1 square n into n plus 1 is 0 for every theta greater than 0. But what is the probability that this is 0? This would be a continuous random variable. The probability that this would be 0 is in fact 0. So you found a function psi t whose expected value is 0. Psi t is basically t is t1, t2. So it is a function of t1 and t2, whose expected value is 0, but probability that psi t is 0. So this is not complete. So let me just stop over here. I would suggest that try to do the homework problems which I gave last time if you have already not done so. We'll have a tutorial tomorrow and we can discuss any of the doubts which you might have from the last homework or the assignment sheet which I gave. I'll be giving you a new assignment sheet based on minimal sufficiency and completeness. That would be due sometime next week. So that's all. If anyone of you have any questions, you may stay back. Others may leave. There is thing that I have not uploaded yesterday's lecture on MOOCit. I have to check. I thought I have uploaded it, but I'll still check. Let me just find it out. Yeah. I'll do both today if I have not done it. Okay. Any doubts? Anyone of you have?
Sir, can you discuss a bit about Laplace transforms?
Laplace transform is exactly like your movement generating function. In fact, uniqueness of movement generating function is a particular result of the uniqueness of a Laplace transform. So let me just share my whiteboard. So let us look at let psi be a function defined on an interval a b to r, right? The Laplace transform of psi is defined as integral over a to b. It would be a function of t. So let me write down Laplace transform at the point t, e to power minus tx times psi of x t belonging to anything. T belong to some domain d, right? For which this integral is finite. This is called a Laplace transform. So you see, if there was in place of minus t, you put t, you get a, and psi is a PDF, then it is nothing but a movement generating function. What you know about movement generating function is that movement generating function is unique. That means if two movement generating functions match on an interval, then the corresponding PDFs, which are the corresponding functions, should be the same. In fact, that is a particular case of this. It says if Laplace transform of a function psi1 is same as Laplace transform of function psi2 in an interval, let us say any interval which a to b, then psi1 would be same as psi2. That is what uniqueness of a Laplace transform says. It is basically same as your uniqueness of mg. So what was happening over here is, for example, if I know that e to power minus infinity or 0 to infinity, let us say e to power minus t theta and a function, let us say f of t dt is 0, and t does not depend on theta, for every theta in some neighborhood, suppose for every theta greater than 0. So what it says, Laplace transform is 0. And 0 is a Laplace transform of a zero function. So two Laplace transforms are matching in an interval. So that means the function should also match. So here, this is a Laplace transform of 50, right hand. That is what it means. Does that clarify your doubt, or?
Yes, I understood. Thank you, sir.
Yeah. So it is same as the movement generating function in certain sense. In mathematics, you name it as a Laplace transform. In statistics, we call it as a movement generating function. And normally in the statistics, we talk about the Laplace transform of a PDF or a probability mass function. Okay?
Yes, sir. Thank you, sir.
Any other doubt anybody has? So if there are no further doubts, let me just stop the meeting here. That's all for today. See you tomorrow for the tutorial.